Hello, everybody. Yes, so my name is Joseph Almeida. I'm a master's student from New Jersey Institute of Technology, and under the guidance of my advisor, Dr. Matthew Bindelt, we've been looking into the behavior of reinforced HPFRCC columns subjected to varying axial load ratios. So we first need to understand what HPFRCCs, or high-performance fiber-reinforced concretes, are. And really, at a high level, these are cementitious and concrete materials that have been reinforced with steel or plastic fibers. And when we do tests at the material level, what we'll typically see is a ductile response in tension. So in contrast to typical concrete, where we'll ignore the tensile properties of the material, what we can see here in the plot below of various HPFRCCs is that these materials offer substantial tensile strain capacity. So when we reinforce these materials with steel, what we'll see is typically enhanced performance at the component level. So to kind of illustrate that concept, we have here two cantilever beams subjected to cyclic lateral loading. What we can see here in the reinforced concrete beam is that there's more spalling. The crack openings are much larger, and just generally there's more damage at the base of the component. In contrast, what we can see in the reinforced HPFRCC beam is that we have finer crack openings, more distributed cracking, and overall just less damage at the base of the component. So this enhanced performance that we see at the component level kind of leads us into our big picture question, and that is, what's the performance, cost, and life safety of these ductile materials at the structural level? And to kind of answer that big question, we need to understand the behavior of columns. And in particular, we're focusing on columns because beams composed of these ductile materials have been well researched, and they've already started to look into how these components behave at the structural level. But columns have been not well understood. There's limited experimental work with these components. So in order for us to understand the full structural response, we need to understand how all the components are behaving in the structure. So in addition to that, we also need to develop structural analysis tools that can capture these ductile material behaviors. So what we did was we employed finite element simulations. So in the middle here, we have our cantilever column that we simulated. We applied a lateral displacement in a single direction and an axial load at the top. And using these finite element simulations really allows us to vary not only the axial load, but the reinforcement ratio and the material properties. And we can see how each design parameter is changing that column response. So we then evaluated the column behavior from our simulations. We compiled the preliminary database of those responses that we got. And we then developed some preliminary expressions for structural seismic analysis. And ultimately, this preliminary work is being used to guide our experimental program. So from our finite element simulations, we obtained our column response. So what we're looking at here is, on the y-axis, the applied moment to the column. And on the x-axis, we have the rotation of that column. At the bottom, we have essentially a column subjected to no axial load. And at the far top in red, we have a column subjected to 25% axial load. So what we can immediately see from these responses is that as we increase the axial load on the column, we get increasing column capacity. And the reason why we see that is, as we apply the axial load, we're relieving those tensile strains on the tension reinforcement. And ultimately, that allows for the column to yield at a higher load. So in addition to the increased capacity, we can also observe the failure mode of these columns. So I've gone ahead and marked out the tension failure with the X and a dot for the compression failure. And what we can see is up to and just below 15% axial load, we actually have tension-controlled columns. And then from there, from 15% axial load, we have compression-controlled columns. And then lastly, what we can observe is, as we increase that axial load, we're seeing higher degradation and a loss of load carrying capacity. So to kind of further understand how much capacity are we losing and how much do we have left to really at that ultimate failure state. So we defined what's called here residual strength ratio, and we took the moment at that column failure divided by the yield moment of that particular column. And we also wanted to understand how this particular residual strength ratio is a function of reinforcement ratio as well as axial load. So we applied that, we plotted that as a contour plot. And what we can first see is that these contour lines are reasonably horizontal, so it's predominantly a function of axial load. And more importantly, what we can see is this dark blue at the top. So column subjected to 25% axial load ratio. We still have 72% of load carrying capacity at failure. So these columns are not just abruptly failing once they reach their nominal capacity. We still have substantial load carrying capacity even at that ultimate failure state. So now to kind of work towards understanding how these columns behave at a structural level, we can't necessarily use our finite element simulations. These are computationally extensive for structural analysis. So what we'll typically do is simplify the structure into a spring hinge model. And each component is essentially modeled as an elastic frame element with a rotational spring at the base. And that rotational spring at the base is actually our moment rotation response of that component. So what we can do is we can take our finite element results, our moment rotation response, and essentially pick key points along that moment rotation response. And we can then use predictive equations to predict those key control points. And we essentially then just connect the dots to get a rough moment rotation response of that column without actually doing finite element simulations. So we went ahead and created some preliminary seismic analysis expressions for those key control points. And from there, we then compared that to not only the very limited experimental data, but we also compared that to existing reinforced concrete expressions to see how these materials and how we would model them change. So in black, we have, the experimental. In red, we have the moment rotation response predicted from our expressions developed from our finite element simulations. And then in blue, we have our reinforced concrete expressions. And what we can see right off the bat is that our proposed HPFRCC expressions can reasonably capture the behavior of the experimental that we're seeing. And what we can also see is that the existing reinforced concrete expressions don't adequately capture the experimental behavior. So some things to note, like we had seen in that contour plot before, is that we still have considerable residual strength after we reach that nominal capacity of the column up till failure. Whereas in the reinforced concrete expressions, what typically happens is once we reach that nominal capacity, we have continued degradation, typically associated with rebar buckling and crushing. And then we typically ignore the residual strength of these columns. So we're not really capturing the and taking advantage of these ductile materials if we were to use existing reinforced concrete expressions. So where are we at really in this project? And really we're going to be still using these finite element results to guide the experimental program. From there, we'll then directly validate and adjust our finite element models. We'll then redevelop our seismic analysis tools with the experimental as well as the numerical data. And then lastly, we'll be able to answer that big question and evaluate HPFRCCs at the structural level. So some key takeaways. HPFRCC columns exhibit ductile behavior even at relatively high axial loads. And existing reinforced concrete expressions don't adequately capture HPFRCC column response. And the big picture of all of this is really to develop accurate seismic models so that we could then evaluate HPFRCC structural performance, cost, and then life safety. So with that, I'd just like to thank you all. I'd like to acknowledge NSF for funding the project, as well as ACI for funding my trip out here. So, thank you.